Hello, welcome to the Chapter 3 CCNA module brought to you by Eduonics. We're going to be having a look at IP addressing. We're going to have a look at describing the operation and necessity of using private and public IP addresses for IPv4. Identify the appropriate IPv6 addressing scheme to satisfy addressing requirements in a LAN or WAN environment. And identify the appropriate IPv4 scheme using VLSM and summarization to satisfy addressing requirements in a LAN and WAN, and describe the technology requirements for running IPv6 in conjunction with IPv4. And again, we're going to go to some IPv6 addressing in general. So each TCP/IP host is identified by the logical IP address that it has. The IP address is a network layer address that has no dependence on the data link layer address, such as a MAC address of the network adapter. A unique IP address is required for each host on the network components that communicates using TCP/IP. I realize a lot of you guys doing this will already know, but we just need to cover the basics as well. The IP address identifies a system's location on a network in the same way that a street address identifies a house on a city block. Just as street addresses must identify a unique residence, an IP address must be globally unique and have a unique format. And each IP address includes the network ID and the host ID. The network ID, also known as the network address, identifies the systems that are located on the same physical network bounded by IP routers. All systems on the same physical network must have the same network ID. The network ID must be unique to that particular internetwork. The host ID, also known as a host address, identifies a workstation, server, router, or other TCP/IP hosts within a network. The address for each host must be unique to the network ID. The network ID refers to any IP network ID, whether it be class-based, a subnet, or a supernet. An IP address consists of 32 bits. Rather than working with 32 bits at the same time, it's common practice to segment the 32 bits of an IP address into 4 8-bit fields called octets, which you can see here. Each octet is converted into a decimal number, the base 10 numbering system, in the range of 0 to 255 and separated by a period or a dot. The format is called a dotted decimal notation, and this thing here gives you quite a good representation of binary versus dotted decimal notation. So that is 192, this is 168, this is 3, and this is 24. So although the conceptual notation of subnetting by utilizing host bits is a bit straightforward, the actual mechanics of subnetting are a bit more complicated. And subnetting requires a 3-step procedure. You need to determine the number of host bits to be used for the subnetting. You need to enumerate the new subnet network IDs and enumerate the IP address for each new subnet network ID. And here we have the class B address. Here you have the network ID and the original host ID. Then you have the number of subnets ranging from 2 to 256 and the number of hosts ranging from 16 to 254. In practice, network admins define the maximum number of nodes they want on a single network. If you recall that all nodes on a single network share all the same broadcast traffic, they reside in the same broadcast domain. Therefore, growth in the number of subnets is favoured over growth in the number of hosts per subnet. And as like a bit of a general rule, you should kind of use these rules to determine the number of host bits to use for subnetting. So you need to determine how many subnets you need now and how many you'll need in the future. Each physical network is a subnet, and WAN connections can also count as a subnet depending on whether your routers support unnumbered connections. You can use additional bits for the subnet mask if you will never require as many hosts per subnet as allowed by the remaining bits, and the number of subnets will increase in the future, requiring additional host bits. To determine the desired subnetting scheme, start with the existing network ID to be subnetted. The network ID to be subnetted can be a class-based network ID, a subnetted network ID, or a supernet. The existing network ID contains a series of network ID bits that are fixed and a series of host ID bits which are variable. Based on your requirements for the number of subnets and the number of hosts per subnet, you can choose a specific number of host bits to be used for subnetting. So this shows the subnetting of a Class A network ID. Now, based on the required number of subnets and maximum number of hosts per subnet, you can get a subnetting scheme together quite well based on this here. So the number of required subnets say is going to be between 9 and 16. Then the number of subnet bits you will have is 4, and your subnet mask will be a /12, which is 255.240.0.0, and the number of hosts you can have per subnet would be 1,048,574. So this is for a Class B network. If you look at the slight differences here between, so say a Class A network on here you have between 9 and 16 you have 1,048,000. Here 9 and 16 you have 4,094. And then a Class C network, you have 14. The number of hosts per subnet will be 14. So as a good note, there's a variety of documented shortcut techniques for subnetting. However, they only work under a specific set of constraints, for example, only up to 8 bits of a class-based network ID. So it's important that you find your own method for doing it, and we'll look at a method here which hopefully you'll find quite useful. So based on the number of host bits you use for subnetting, you must list the new subnetted network IDs. There are two main approaches to doing it: binary, which is listing all the possible combinations of the host bit chosen for subnetting and convert each combination to a dotted decimal notation, or decimal, add a calculated increment value to each successive subnet network ID and convert to dotted decimal notation that way instead. And either method produces the same result, the enumerated list of subnets via network ID. So step number 3 is enumerating IP addresses for each subnet network ID. Now, I've just decided to look at Microsoft TechNet here because they have a great explanation for it, and I'd rather use theirs than having to try and bastardize my own from theirs. So let's take a look at this. Okay, so step 3 here. So to create a range of IP addresses using the binary method, based on the n, the number of host bits chosen for subnetting, create a 3-column table with 2 to the power of n entries. The first column is the subnet number starting with 1. The second column is the binary representation of the first number and last IP address for the subnet network ID. And the third column is the dotted decimal representation of the first and last IP address of the subnetted network ID. Alternatively, add 2 columns to the previous table used for enumerating the subnetted network IDs. And for each binary representation, the first IP address is the address in which all of the host bits are set to 0 apart from the last host bit, and the last IP address is the address in which all the host bits are set to 1 except for the last host bit. Convert the binary representation to a dotted decimal notation and then repeat steps 2 to 3 until the table is complete. So for example, the range of IP addresses for the 3-bit subnetting of a 192.168.0.0 is shown here. And to do it via dotted decimal notation, it is pretty much the same. And then you can compute the incremental value, which is j based on 8, the number of host bits remaining. And then for each decimal representation, the first IP address is n plus 1, where n is the decimal representation of the subnetted network ID. The last IP address is, again, n plus j. We'll cover that in a bit more because I know that's not exactly the best explanation or the easiest to follow.